This is 3I Atlas, an interstellar object that entered our solar system from beyond our star. Unlike asteroids or comets that formed alongside the Sun, this object originated around another star entirely. It spent an immense amount of time traveling through interstellar space, isolated from any planetary system, before briefly crossing into our cosmic neighborhood. What you are seeing here is not speculation. It is the result of ongoing observation, careful measurement, and repeated verification. And even now, scientists continue to collect and refine new data. Over the past month, telescopes across the world and in space have been tracking 3I Atlas continuously. Each observation improves our understanding of its position, its brightness, and its activity. Early detections always carry uncertainty, but as more data points are gathered, patterns begin to emerge. With enough observations, models become more reliable, and predictions become more precise. Current tracking confirms that 3I Atlas follows a hyperbolic trajectory. In simple terms, this means it is not gravitationally bound to the Sun. It did not originate here. It entered the solar system at high speed, passed through the inner regions, and is now clearly on an escape path. This orbital behavior alone confirms its interstellar origin beyond reasonable doubt. As 3I Atlas moves through space, its position relative to Earth and the Sun constantly changes. This changes the angle at which sunlight reflects off its surface. These phase angle variations may appear subtle, but they are scientifically important. They help researchers study surface texture, dust distribution, and how light interacts with material that formed around a completely different star. Distance from the Sun plays a major role in shaping the object's behavior. As 3I Atlas moves farther away, solar heating weakens. Gas and dust production slowly decrease, and the visible coma and tail evolve over time. This pattern is consistent with volatile-driven cometary activity. At the same time, it provides rare insight into how material from another star system responds to stellar heating for the first time. Spectral observations allow scientists to look beyond appearance and study composition. By analyzing how light is emitted and absorbed, researchers can identify gases released from the surface. These spectral signatures act like chemical fingerprints. They allow comparisons between interstellar material and known solar system comets, revealing both similarities and important differences. Brightness variations over time offer another crucial piece of information. Small repeating changes in brightness allow scientists to infer how 3I Atlas rotates. These light curves suggest a stable rotation rather than chaotic tumbling. Rotation influences how sunlight heats the surface, how jets form, and how material is released into space. Understanding rotation is essential for building accurate physical models. When observed brightness is compared to baseline theoretical models, differences naturally appear. These differences are expected. They result from dust production, viewing geometry, surface roughness, and particle size distribution. Brightness analysis helps refine size estimates and improves understanding of the object's internal structure. 3I Atlas is not studied in isolation with earlier interstellar visitors. While each object is unique, shared characteristics emerge over time. Hyperbolic orbits, volatile-driven activity, and short observation windows appear to be common features. With every new detection, scientists improve their statistical understanding of how common interstellar objects may be throughout the galaxy. Early observations always involve uncertainty. This is a normal part of scientific discovery. But as data accumulates, confidence grows. Error margins shrink. Predictions improve. In the case of 3I Atlas, continued monitoring has already placed strong constraints on its trajectory, its activity, and its physical interpretation. At present, several key parameters are being monitored closely. Brightness stability reveals ongoing surface behavior. The nucleus. Dust decay tracks how particles disperse over time. Spectral consistency helps determine whether composition remains stable as activity declines. Together, these measurements create a comprehensive physical profile. As 3i Atlas continues its journey, viewing geometry will continue to change. Certain alignments provide clearer observational conditions. These moments allow scientists to extract more detailed information about structure, composition, and evolution. Such observation windows are carefully planned and actively studied. Interstellar objects are scientifically valuable because they are natural samples from other star systems. They help scientists understand how planets form elsewhere, what kinds of chemistry exist beyond our sun, and how dust and ice evolve across the galaxy. Information from a distant stellar environment that we could never otherwise reach. Even now, observations continue. Models are updated, predictions are refined, assumptions are tested. Science does not end with discovery. It improves with time, with patience, and with evidence. If you enjoyed this deep dive into real space science, like the video and share it with others who are curious about the universe. Subscribe to the channel for future updates because the cosmos always has more to reveal.